Okay, welcome back to 15-Minute Math. So we have worked with limits a little bit in the last few videos, and we've kind of just thought of them as the completion of a pattern in a way, whether we're dealing with sequences, which are kind of one-dimensional, or we're dealing with functions, which, you have an x and y component, but we're still thinking about just kind of completing a pattern, right? We're getting very, very close to some specified number. And the y values are making a pattern, and we're going to try to kind of fill in the gaps. We're trying to complete the pattern. Or if we're dealing with sequences, then we're not really looking at a specific x value. We're just saying, okay, as the sequence goes on and on and on, where are the terms of the sequence converging to? What number are they getting closer and closer to? And that was just kind of our idea of the limit. And we weren't real formal with it, and that's okay. It's good to have that intuition in your head. And the problem is when functions get maybe a little more advanced, and they're not just the elementary functions that we tend to deal with in high school. They're not just polynomials, trig functions, exponentials, those sorts of things. You get a little more exotic, and that sort of loose definition can get you in trouble. And people after Newton's times, of course, Newton and Leibniz were the two that kind of were at least get credit with founding calculus, and neither of them really formally defined a limit. They just kind of had this fuzzy intuition, kind of like what we did before. And mathematicians a little bit later after their day ended up getting into trouble because they started digging deep into some more advanced functions, and they needed a precise definition. And after a little bit of wrangling with what that precise definition is, this is kind of what mathematicians have come up with. So let's read the definition, then we're going to break down the definition, and then towards the end we're going to see how this definition it really kind of just makes what we already have in our heads just very well defined and airtight, and so that there can't be any sort of screwy situations that kind of break our definition. So here's the definition. Let I be an open interval containing C, and let f be a function defined on I, except possibly at C. So what we're saying here is we have some function defined on some domain. Now in calculus, in the high school level or first semester college, most of the time I is going to be all the real numbers, or maybe all the real numbers with the exception of a couple points. Like, for example, on a rational function, you'd have all the real numbers except for where you divide by 0. So there might be a few exceptions. But generally, just think about I as being the real number line, okay? And then our function is just defined on that number line, except for maybe at C. We've already seen a few instances where the function's not defined at C, but we still have a limit. So that's all that's saying right there. It's kind of the setup there. So it says the statement, and then that's our normal limit statement, right? This statement right here, that's what we usually see. F of x is usually some function. L is just some number. C is that x value that we're kind of concerned with. So that statement means that given any epsilon greater than 0, there exists delta greater than 0, such that these inequality, or I should say, such that this inequality implies that inequality. And I think what's going to help us here is to, instead of think about it symbolically, we're just going to think about it in words here. So notice that this absolute value statement, think about what an absolute value tells you. An absolute value is just the distance between two things, where like the positive and negative doesn't matter, right? It doesn't matter if x is bigger than C or C is bigger than x. If I take the absolute value of their difference, I'm just thinking about the distance between those two. So that is just the distance between x and C. And notice this has to be bigger than 0. So I'm gonna call this, let's write this out in words. This just means the non-zero distance between x and C is less than delta. I know I haven't really explained what delta is, but we will get there. But for now, I'm just trying to translate the math notation into kind of readable English. So that's what this inequality tells us, and that should imply, or that should mean, that this inequality is true. And again, we have these absolute values, but we want to think about that as a distance. So this implies that the distance between f of x and L is less than epsilon, which again, we haven't explained what epsilon is, but just bear with me here. And I think this inequality maybe takes a little more explaining. So when you think of f of x, you should think about like the y values that you're getting out of your function. And of course, L is the limit that we're concerned with. Okay, and so we're just saying that the difference between the y values and the limit is less than this epsilon character. Okay. And so now we should probably explain what do we want to think about when we think about delta greater than 0. What are we thinking about? Okay. And so the idea is this, and I'm going to maybe sketch a graph. We will go over to Desmos. Don't worry. I know you're wondering when we're going to switch over to Desmos. It's coming. Just hang on for a moment. We're going to do some hand sketching first. Okay. For some reason I made my XY axis green. You know what? I don't like that. We're going to go over this in black. Zzz. The only reason I don't like that is I already underlined my delta in green, so I want to use green for delta. There we go. Okay. So there's my XY axis. Let's draw a function cruising through our axis here. Oh, let's see, I don't know. Maybe a cubic looking guy. There we go, we'll call him f of x. And let's pick a point that we want to find the limit of. So right now we'll just say this value, we'll call this place on the x-axis, that's going to be C. That's going to be our limiting point. That's where we're concerned with. We are approaching right here. And so maybe it'll be helpful to kind of, where does that correspond to my function? So L would be about right here. Right? Remember, L is our limit. So if I just kind of think back to the video when we're estimating limits graphically, you know, I'm approaching from the left side, I'm approaching that point. From the right side, I'm approaching that point. And so it looks like that function value there is going to be my limit. Okay. And so what we want to think about with these epsilons and deltas, they're kind of like forming a box around my point. And delta is the x-axis box. And so it's saying for any range that we pick that includes C, so maybe we pick a range here. Actually, I'm sorry, I'm maybe getting ahead of myself. Let's start with epsilon. So epsilon, it says for any epsilon greater than 0. So it says, okay, epsilon is a range, but that's a range on our y value. These epsilons, my y values, or maybe I should say y value box, and delta is going to be my x value box. Okay, and so what this means is if I draw like a, you know, an interval that includes L, and I just kind of what this definition means is for any range that we pick here, we ought to be able to pick another range on the x-axis And we should be able to pick it small enough so that if we were a point cruising around on our function, as soon as we got inside of our delta range, we would also be inside of our epsilon range. So as soon as we get inside of the green range, we should also be inside of the blue range, which you could see this delta doesn't really work, right? Because if I was a point and I was allowed to slide along the function, and I got to right here, I've crossed, well, I'm about to cross my delta range, but I'm not quite inside of my blue range, and so that's a bad delta to pick. But notice that for this function, I could just pick a smaller delta. It's hard to draw it, but you'll see it on the Desmos graph, and we might as well go over there because we are down to 4 minutes. Okay, so I have a nice cubic looking graph here. Let me turn off my ranges here. And so here's my function. Let's say we were going to take the limit at 4. So let me put C at 4. So that's our C value right there. So notice that my L is like 2.8. You know, it's this value kind of right here. So our epsilon region, notice here, so there's our epsilon region, and notice I can increase the region. And what this definition says is that for any epsilon that I pick, I ought to also be able to pick a delta region so that if I'm a point cruising along this function, as soon as I get inside of my delta region, which is the black one, I should also be inside of epsilon. So right now this fails, right? Because I'm inside of delta but not epsilon. But why don't I just pick a smaller delta? So there we go. I just picked a super tiny delta, and now it works, right? And if I make epsilon smaller, well, so what? I could just make delta smaller, and it still works. And so the idea is like we can just kind of progressively make each of these smaller and smaller and smaller, and we can make an infinitesimally small box that boxes in our limiting point, and that kind of like zeroes it in, and we boxed in our limit to be 2.8. And you're probably thinking, well, so what? Couldn't you do that with literally any function? And the answer is no. Functions where the limits don't exist, you can't do this. And I'm going to put this video on pause and make maybe like a piecewise function and show you why you can't do that with every single function. Okay, so now I've got a piecewise function to look at. We're going to take the limit as x approaches 4, and notice this limit does not exist, right? Because if I approach it from the left, I would get 3, it looks like. And if I approach it from the right, I'm going to get 5. And so those don't match. And we were going to say the limit doesn't exist. But let me show you why, from an epsilon delta perspective, this would also fail. So let's turn on our epsilon range. Let's turn on our delta range. And let's make C really close to our limiting point. I can't get exactly on it. Desmos is going to freak out. But notice that, well, right now my delta region's too big, right? There we go. Now my delta region works. But this works from the left side, right? As soon as I'm inside of my delta region, as soon as I'm inside of my delta region, I'm also inside of epsilon, so it works, so it passed the test if I was only looking at the left side. But look, if I approach it from the right side, wait, no, not delta, I want A, there we go. If I approach it from the right side here, as soon as I get inside my delta region, I'm not even close to being inside the purple region, am I? It's way the heck up there. And furthermore, it doesn't matter how small I make delta. I can make delta super, super tiny. If I'm coming in from the right, clearly I'm never going to be inside this purple region coming in from the right, no matter how small delta is. So this fails. And so that's why we say, from an epsilon delta perspective, that functions like this, the limit can't exist, because you can't box in your point like you can with a continuous function. So this idea is pretty powerful. It's a great definition. I love this definition. I think from a high school calculus perspective, you won't use it that much, but it is good to see a precise definition of a limit, because I think a lot of the times we kind of use these fuzzy, intuitive ideas, which are good. It's good that you have the idea, but it's nice to have a precise definition as well.